Imagine a burst of energy so powerful that it eclipsed an entire galaxy for a moment. A burst of unimaginable power that traveled billions of light-years to reach us, whose origin is still shrouded in mystery. It's not just sci-fi, it's the reality of gamma-ray bursts, the most energetic events known in the universe. On October 9, 2022, astronomers discovered something unprecedented: the brightest gamma-ray burst of all time, or B.O.A.T, so unusual that it disproved all our ideas about this cosmic phenomenon. But the story of GRB2219A is not just about brightness. It's about the questions it raises, anomalies in its spectrum, the unexpected absence of heavy elements, and new challenges to our understanding of how the most powerful explosions in the universe happen. What caused this colossal explosion, and what secrets can it reveal about the forces shaping our universe? The universe is a realm of unusual phenomena, some of which challenge the very limits of our understanding. Prominent among them are gamma-ray bursts, GRBS, some of the most powerful and mysterious explosions known to science. Discovered quite by accident in 1967 by U.S. military satellites, gamma-ray bursts were initially shrouded in mystery. Because of their intense energy release, they initially raised fears of nuclear testing. However, as their cosmic origin became clearer, GRBS quickly evolved from a classifying mystery to one of the most studied astrophysical phenomena. There are two main types of gamma-ray bursts: short GRBS, which last less than 2 seconds, and long GRBS, which can last up to several minutes. This division is not merely academic, it reflects the different underlying physical processes. Short GRBS are usually associated with neutron star collisions, while long GRBS, like the one observed in October 2022, are associated with the cataclysmic collapse of massive stars. The event in question, dubbed the Brightest of All Time, or B.O.A.T, occurred in the constellation Saga. Detected on October 9, 2022, this gamma-ray burst was unlike anything observed by astronomers before. Its brightness 10 times greater than all previously recorded GRBS shocked the scientific community. What made this event even more amazing was its duration. It lasted 10 minutes, and the afterglow was visible for more than 10 hours. Most outbursts disappear from view within a few seconds or minutes, making B.O.A.T an exceptional event. But beyond the spectacle, the B.O.A.T event has profound implications for our understanding of the universe. Gamma-ray bursts are, by their very nature, windows into extreme conditions that cannot be.
They allow scientists to investigate the fundamental laws of physics, especially when matter is subjected to intense energy and gravitational forces. The B.O.A.T event, so bright and so close, provided a unique opportunity to study these extreme conditions in unprecedented detail. The resulting data opens new avenues for understanding not only gamma-ray bursts, but also the very processes that govern the life and death of stars. The brightest of all time, GRB2219A, then stood out not only for its staggering intensity, but also for its amazing duration. The explosion was so powerful that it was the brightest gamma-ray burst ever recorded, lasting 10 minutes and leaving an afterglow visible for over 10 hours. Such an event, at a distance of only 2.4 billion light-years, is not just rare, it's almost unprecedented, occurring only once every 10,000 years. What makes this outburst truly unique is the combination of extreme brightness and prolonged visibility. Most GRBs are fleeting, often only detectable for a few seconds or minutes, but in contrast, GRB2219A lasted much longer. High-energy emissions lasted for tens of thousands of seconds. This duration provided an unprecedented opportunity for observations and analysis over a wide wavelength spectrum, from X-rays to gamma rays. The B.O.A.T's brightness was so intense that it caused a saturation effect in numerous instruments, including the GBM and lat. These instruments, designed to capture and analyze high-energy photons, were overwhelmed by the power of the event, resulting in significant noise and data delays. Notably, the 400 GeV giga-electron-volt photon was detected nearly 10 hours after the initial burst, indicating unusually high energy levels. Despite its stunning brightness and duration, this event also presented us with significant challenges. Spectral analysis showed that the peak energy of the flare reached about 15 MeV mega-electron volts at the very beginning and then gradually decreased over time. However, what puzzled scientists was the discovery of a B.O.A.T-related supernova, which turned out to be surprisingly ordinary. Given the extreme nature of the GERB, one would expect its progenitor supernova to be equally extraordinary. Instead, the detected supernova turned out to be unremarkable. Moreover, it even lacks signs of heavy elements, which are usually associated with such powerful explosions, but more on that later. These unexpected discoveries led to several hypotheses, one of which suggests that the relative position of the Earth to the GERB may have played a crucial role in the concentrated detection of gamma rays. The narrow jets emitted during the explosion were likely pointed almost perfectly toward Earth, making the event appear much more intense than if the jets were slightly off-axis. This alignment, combined with the GERB's power, created the perfect storm that resulted in B.O.A.T being recorded as the brightest GERB ever observed. In addition, the detection of such high-energy photons raises intriguing questions about the mechanisms of radiation. Conventional models cannot fully explain the observed unusual energy levels, leading some researchers to consider the possibility of new physics, such as interactions with dark matter particles. While these ideas remain speculative, they highlight the potential of GERB 2219A to expand our understanding of the universe, and directions we've yet to fully comprehend is immense. The formation of gamma-ray bursts is closely intertwined with the life cycle of massive stars. When a star several times the mass of the Sun exhausts its nuclear fuel, its core can no longer support the weight of the outer layers. This catastrophic collapse leads to a supernova explosion, but in some stars, it also leads to the formation of an incredibly dense black hole. When matter from a collapsing star falls into a black hole, strong magnetic fields turn some of that matter into narrow, focused jets that fly outward at nearly the speed of light. These jets are the engines of gamma-ray bursts, and their orientation relative to the Earth determines whether we can observe GERBs. In the case of the B.O.A.T event, the jets were particularly narrow and pointed almost directly at Earth. Normally, GERB jets scatter somewhat as they pass through space, but in the B.O.A.T event, the jets remained exceptionally concentrated, concentrating their enormous energy into a smaller area and resulting in more intense emission. The influence of these jets extends far beyond their place of origin. When 2219A erupted, its intense gamma rays reached Earth and interacted with our planet's atmosphere in surprising ways. One of the most significant effects was a temporary compression of Earth's ionosphere, a layer of the atmosphere containing a high concentration of ions and free electrons. This compression was akin to the effect caused by a large solar flare, when the ionosphere is bombarded by solar particles, causing communication systems and satellites to malfunction. However, the gamma rays from the B.O.A.T event were much more energetic than those normally associated with solar flares. The energy of the burst was enough to cause noticeable changes in the ionosphere, even at altitudes where such interactions rarely occur. Observatories around the world quickly detected these changes, leading to a flurry of data analysis to understand the full impact of the GERB on Earth's atmosphere. The data collected during this event has given scientists new insights into how such bursts can affect planetary atmospheres, particularly the interaction of high-energy photons and their potential to affect atmospheric chemistry and dynamics. At the chemical level, gamma-ray triggered reactions in the atmosphere produced additional nitrogen oxide and other reactive nitrogen species. These molecules play a critical role in ozone chemistry, particularly in the destruction of ozone in the upper atmosphere. Although the exact effect on global ozone levels has not yet been studied, such bursts may contribute to local or temporary changes in ozone concentration, potentially affecting the protection of the atmosphere from harmful ultraviolet radiation. However, these observations have also raised new questions. The unprecedented strength and narrowness of the B.O.A.T event jets challenge existing models of GERB formation and propagation. Standard models predict a certain degree of jet spread, which helps disperse energy over a wider area. But the B.O.A.T event jets have disproved these expectations, suggesting that, under certain conditions, jets can remain tightly focused over much greater distances than previously thought. According to modern ideas, the extreme energy and rapid rotation of the collapsing star played a key role in this. The intense magnetic fields produced by the star's rotation probably contributed to the collimation of the jets, preventing them from spreading out in space. In addition, the lack of significant interference from surrounding matter may have allowed the jets to maintain their tight focus over vast distances. These findings not only challenge our current models, but also hint at the possibility of previously undetected GURBs with similarly focused jets that may have been missed by our instruments due to their directional nature. A better understanding of these mechanisms may reveal new classes of GURBs and their potential impact on both the local environment and distant planets, including Earth. However, let us return to the question of how the outburst is related to the formation of elements in the universe. It's simple. The formation of elements in the universe is history written in the hearts of stars. Inside a star, nuclear fusion works like a cosmic forge, turning light elements such as hydrogen and helium into increasingly heavier elements. This process continues until the element iron is formed. At this point, the fusion process no longer releases energy, it requires more energy than it produces, leading to a catastrophic imbalance. The star can no longer support its weight, leading to its eventual collapse and often to a supernova explosion. While fusion in stars easily produces elements up to iron, much more extreme conditions are required to create elements heavier than iron, such as gold. These heavier elements are formed primarily by a process known as fast neutron capture, or the R process. During the R process, a dense environment with a high neutron flux allows atomic nuclei to rapidly capture neutrons, creating increasingly heavier elements in a very short time. This process is best known in neutron-star collisions, where the enormous energy and neutron-rich environment create ideal conditions for the R process to occur. The event confronted scientists with the unexpected fact of their absence. Despite the extreme energy and conditions seemingly ripe for nucleosynthesis in the R process, no evidence of heavy elements was detected in the supernova spectrum. No gold, no platinum, none of the things one would expect from such a powerful event. This absence raises important questions about our understanding of how and where the heaviest elements in the universe are formed. This surprising result suggests that not all collapsers are prolific producers of heavy elements. Perhaps the conditions required for significant nucleosynthesis in the R process are even more specific than we thought, and may only occur under certain conditions within these already rare events. On the other hand, this could mean that other processes or conditions related to neutron-star mergers play a more significant role in enriching the universe with heavy elements. Another interesting thing about the brightest of all time is that it may well shed some light on the nature of dark matter. According to one intriguing hypothesis, dark matter may consist of particles called axions, hypothetical particles that have not yet been directly observed. The idea that photons, particles of light, can turn into axions as they travel through space is a tantalizing one. If true, it could help explain why dark matter is so hard to detect. Perhaps it's hiding in plain sight in the form of photons that turn into axions and elude our instruments. The B.O.A.T event, with its intense burst of gamma rays, provides a unique opportunity to explore this hypothesis. As these gamma rays spread across the vastness of space, some of them may have interacted with cosmic magnetic fields, becoming axions. This process could reduce the flux of gamma rays reaching Earth, a subtle signal that could hint at the presence of axions. Although no definitive evidence for the existence of axions was found in the B.O.A.T event data, this possibility remains an interesting avenue for further research. If further observations of such events reveal patterns consistent with the conversion of photons into axions, this could be a breakthrough in our understanding of dark matter and open the door to new physics beyond the standard model. As we look to the future of astrophysics, the study of gamma-ray bursts remains a cutting-edge frontier full of promise and mystery. Current missions, such as NASA's Fermi Gamma Ray Space Telescope and the European Space Agency's Integral, continue to play a critical role in detecting and analyzing GURBs. But the next generation of missions will push the boundaries even further. Projects such as the Chinese-French SVAM mission and NASA's upcoming COSI mission are designed to provide unprecedented insight into the high-energy universe. These missions will aim to detect the most extreme cosmic events and will allow us to collect data with greater precision, potentially unlocking new physics and deepening our understanding of the mechanisms behind these powerful explosions. Will future observations reveal the elusive nature of axions, or perhaps identify the specific conditions under which the heaviest elements are formed? These are the questions that define the next steps in the exploration of the universe, guiding us toward a deeper understanding of the cosmos and our place in it. Events like B.O.A.T serve as milestones in the development of astrophysics, reminding us that the universe is much more complex and dynamic than we can currently understand. Each discovery forces us to ask new questions and propels our quest for knowledge forward, and who knows, perhaps the answers to these mysteries are just a cosmic explosion away, waiting to be uncovered by curious minds. In the meantime, we will continue to keep you up to date with new developments. Stay inquisitive, and until next time. Today, we're going to talk about one of the many interesting stories lying in the depths of space. It is a story not about luminous stars or spiral galaxies, but about the most mysterious and dense objects in the universe, neutron stars. Our story begins with a violent and colorful ending, a supernova explosion. In this spectacular celestial fireworks display, the death of a massive star gives rise to something extraordinary. From the heart of this cosmic eruption, a neutron star is born. The stellar remnant is so dense that just a teaspoon of its material weighs as much as a mountain. But what happens when these stellar remnants, these neutron stars, are not alone? What secrets do they reveal when they collide in a catastrophic confrontation between gravity and light? Today, we'll witness extreme physics in action, explore the rippling fabric of spacetime, and hear the whisper of the universe through gravitational waves. In the vast cosmos, the life of a star is a story of transformation and energy. Our story begins with the colossal star, much more massive than our sun. At the core of this giant, a fierce battle rages between gravity and nuclear forces. This star, like all stars, is a nuclear furnace. In its core, hydrogen atoms fuse to form helium, releasing enormous amounts of energy. This process of thermonuclear fusion is the basis of a star's life.